Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we'll review everything you need to know for the upcoming test about networks. So what are networks? Well, they're just things that look like this. They're just a sequence of vertices or nodes and edges, the things that connect them. So these can represent anything. For example, I've just gone with an example of country towns. So each of these vertices would be a different town, and the edges, the things connecting them, would be like a road. So in this network, you can see there are 1, 2, 3, 4, 5, 6, 7 vertices representing different towns. And the number of edges connecting them, there's 4, 5, 6, 7, 8, 9. So this is a network with 7 vertices and 9 edges. We just need to get a few definitions down. So is this graph connected or unconnected? So connected means that it's possible to go from any vertex to any other vertex. So in this case, it's possible to start at any town and go by road to any other town. That makes this graph connected. You can start anywhere like B and you can get anywhere you want. Say F, you might have to go through a few other towns, but that's okay. So this graph here is connected rather than unconnected. Just so you know, an unconnected graph would be if I have something over here, like a vertex by itself, that cannot be accessed from any of these. But because I didn't include such a vertex, this is a connected graph. And just so you know, networks are also called graphs. I use the terms interchangeably. So is this a directed or undirected network? So when we have a directed network, you will see arrows along these. So they happen in things like water flow network, series of pipes. If you see arrows along these, an arrow like this, it means that travel is only possible in one direction across an edge. But because I didn't include any such arrows, it means that travel is okay in both directions along an edge. You can go from B to G or G to B. So that actually makes this one an undirected graph. So again, undirected graph or network just means that there are no arrows along the edges. It means that travel is possible in both directions. Is this a weighted or unweighted graph? Well, that's actually easy to tell. Weighted graphs have numbers along the edges. Unweighted graphs don't. So this is clearly a weighted graph. So these numbers represent something. In this case, because we're talking about towns and roads, these will be the distances between towns. So for example, A and B are 55, say, kilometers apart along this road. So this is a weighted graph because there are numbers on each edge. So does this graph or network contain any cycles? So cycles is a concept where it's much easier to see rather than it is to explain. What it actually means is a set of unduplicated consecutive vertices. What does that mean? It means that you can go from A back to itself without visiting any of the other vertices twice. So A, B, C, and D is an example of a cycle, but this graph has many cycles. You can see that B, G, and E form a cycle. Turns out A, B, G, E, D, C, A, that forms a cycle too, because you can start at A, go through each of these vertices only once, and end up back where you are. So make sure you don't confuse cycles with loops. Loop is actually when you have a vertex connected to itself, when you have an edge that goes from a vertex back to itself. So a loop would look something like that. That's an example of a loop, an edge that goes from A back to A. But I actually didn't include any of those in this network. So this is a network that has many cycles, but it has no loops. So we also need to know when looking at a network whether an Eulerian path is possible and whether an Eulerian circuit is possible. So Eulerian paths, if you've forgotten, are paths that go through the whole network, visiting each edge once and only once. So that means they travel along each of these edges, but they never travel along any of those edges more than once. So to determine whether or not an Eulerian path is possible, we need to look at the degrees of vertices. So the degree of a vertex is just the number of edges emanating from it. So if we look at vertex A, there are 2 edges from A. So we say that the degree of A is equal to 2. Similarly, the degree of F is equal to 1 because there's only 1 edge from it. The degree of E is 4 because there are 1, 2, 3, 4 edges starting at E. So to determine whether or not an Eulerian path is possible, we need to know the degree of each of the vertices. So A, C have degree 2, B has degree 4, D has degree 3, E has degree 4, G is 2, and F is 1. In this network, there are exactly 2 vertices, D and F, that have an odd degree. So an Eulerian path is possible. It's actually possible to draw a path here that visits each edge once and only once. Now, when there are 2 vertices of odd degree, to draw an Eulerian path, you start at one and finish at the other vertex of odd degree. So in this one, we'd have to either start at D or start at F and finish at the other one. If all vertices have even degree, you can start wherever you like. So let's draw an Eulerian path starting at D. So we want to go through every edge once and only once. So we could go there, 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 like this, all the way around. See that I've only visited each edge once and only once. So we write such a path like this. This is just the sequence of vertices that we take. So we started at D, C, A, B, G, E, B, D, E, F. Notice in an Eulerian path, it's okay to visit vertices more than once. We just can't travel along an edge more than once. So this is an example of an Eulerian path. There are other Eulerian paths. We could find others starting at F, for example. There's more than one that starts at D, more than one that starts at F. So would an Eulerian circuit be possible? Well, an Eulerian circuit is the same as an Eulerian path, but it starts and ends at the same vertex. So this Eulerian path here is not a circuit, because we didn't start and end at the same vertex. We started at D and ended in F. So it's actually not possible to draw an Eulerian circuit here. Rather than using trial and error, let's just go back to our rule involving degrees. An Eulerian circuit is possible only when all vertices have even degree, because the degree of D is 3, degree of F is 1. We have 2 vertices that have odd degree, and so an Eulerian circuit is not possible. It is not possible to draw an Eulerian path that starts and ends at the same vertex. And that's because of what I said before. When you have 2 vertices of odd degree, any Eulerian path starts at one of those vertices and ends at the other. All right, what about Hamiltonian path and circuit? So a Hamiltonian path is similar to an Eulerian path, but rather than going along each edge once and only once, we visit each vertex once and only once. So you can never visit a vertex more than once in a Hamiltonian path. So it's not as clear-cut for Hamiltonian paths when they are possible, but they often are. We can draw a Hamiltonian path easily. Starting at F, we can go along like this, and this gives us a Hamiltonian path because I have visited each vertex once and only once. So this sequence of vertices I took for this Hamiltonian path, I went F, E, G, B, A, C, D. That is a Hamiltonian path. But it turns out, just like the Eulerian circuit wasn't possible, neither is the Hamiltonian circuit. It turns out a Hamiltonian circuit is never possible if you have a vertex of degree 1. So why is that? Well, remember, a circuit is the same as a path, but you have to start and end at the same vertex. So if we start at F, you can see that we're not going to be able to finish at F. We can't visit F twice, start and finish there, without going to E twice. So what about if we started at another vertex? Well, we'd end up getting the same problem. No matter where you start, you have to visit E in a Hamiltonian path. And that would mean that we would have to go to E, and then we'd have to go back to E after F. So the point is, we can't have a Hamiltonian circuit when we have a vertex of degree 1, because it would mean that we would have to visit this vertex here more than once before ending. That's why it's not possible. So another question you need to be able to do is find the shortest path from A to E. So that's not going to be too difficult. All we have to do is look at the numbers and the different paths. And don't worry, you're not going to get a network with a million different vertices and edges. So from A to E, there's a few different ways we can go. We can go this way, which has a distance of 73, 55 plus 18. We could go 20, 32. That has a distance here of 68. The shortest path is 55, 65, 67. So the shortest path from A to E is going A to B to G to E. That whole distance is 67 kilometers. All right, let's look now at a few harder questions. So an undirected graph is such that each vertex is connected to each other vertex. That means there is an edge from each vertex to every other vertex. There are 8 vertices, and we're also told half of them are connected to themselves. How many edges are there? So for each of the 8 vertices, there would be 7 edges, 1 to each of the other 7 vertices. So we've got 8 times 7, or 56 edges. But in an undirected graph, we need to divide by 2, otherwise we're double counting edges. So for example, if I have a network like this, A and B, and there's an edge between them, I can't count this edge when I'm looking at the edges from A, and then count it again when I'm looking at the edges from B. That doesn't make any sense. So that's why we need to divide by 2. So it's just the number of vertices times number of vertices divided by 1 divided by 2. So there are going to be 28 edges in total from each vertex to a different vertex. However, we're also told that half, so 4 of these vertices, are connected to themselves. So there'll be 4 extra edges from vertices to themselves. So the total number of edges is just going to be 28 plus 4, which is 32. So now it says, what would be the sum of the degrees of the vertices? So whenever you have an edge like this, you can see that it increases the sum of the degrees by 2. A, its degree is increased by 1, degree of B is increased by 1. When you have a loop, so an edge to itself like this, it actually counts as increasing the degree by 2. So in this small network, B actually has degree 3, 1, 2, and 3. So the sum of the degrees of the vertices is always going to be double the number of edges. Again, that's because each time you have an edge, it increases the degree of its start and end vertex. It increases the sum of all of the degrees by 2. All right, thank you so much for tuning into this video. Best of luck studying, but you will ace the test. This has been the luckiest maths teacher in the world. Have a great day.